Alright, I'm going to try to make this a quick video and not get too far into the details, but here we're going to start out. We're going to look at which of the following set is not a relation between n and r, and of course being the natural numbers, r being the real numbers. And it's a little bit hard to see if you zoom in. This is a 0.1. It's not like a 1.01 or anything like that. But whenever we have a relation between one number to another number, when we do the cross product, we always end up with some element from A and then some element from B. So A in this case would be the natural number, B would be R, the real numbers. So what that basically means is that the first number in this ordered pair should always be a natural number. And we can see here we have -1, so clearly that is not the case. Meanwhile, we can see that the second item of every ordered pair is in fact a real number. 7.8 is a real number, -19. Real number encompasses a lot of different things, including fractions and decimals and all that. But because we have this one instance of -1 being where we should be having the natural numbers, clearly that is incorrect. But let's look at the other options real quick. It could have been the empty set. It is not, because the empty set is a relation on every set, basically by the same vacuous logic that we use to determine that the empty set is a subset of every set. So therefore, we're going to say that this is, in fact, a relation between n and r. Here we have 33, 55, 0, 28, 38 in the first entry, and we can see that every time it is a natural number. 5, 97, also all natural numbers. And if we look here, everything that we have on the second entry for each one of these ordered pairs is in fact a real number. So we can go ahead and move on from that. This is the correct answer, mainly because of this negative right here. The first number should always be n, and the second number should always be r. The empty set is a binary relation on humans, and again, this is the fact that the empty set is a relation on all sets. Therefore, like, most things with the empty set, we can say that this is vacuously true. So that is all you really need to know. Relation composition is associative. Let's talk about what that is, because I haven't done a video on it. Relation composition basically just means if we have two different ordered pairs, like 3, 2, and we'll call this one set of pairs, and then we have another set of pairs, like, the composition is basically going to be kind of a transference. Without getting into the mathematic, definition of it, we're just simply looking here. We see that we have a 3 here, and then that is going to map to a 2. So what we would do is we would look over here to see if we have a 2. We do not, so therefore 3 is not going to be in the composition. However, here we can see we have a 5 being mapped to a 7. We look over here, we see that we have a 7 and a 6. So therefore, the composition here is going to be 5, 6. And all we're really doing is looking at this number and seeing if that number is in this set as the first ordered pair, and then replacing it with the second number. And we do that for every number. If we had another pair, like for example, if we had 8 and 1 in this set right here and 1 and 2 in this set, then we would also include in our composition set that we have 8, 2. Because we start here at 8, we look here, we see that we have a correlated value here for 1, so we're going to take that second value and we're going to put that in our composition. Although associative basically means that it doesn't necessarily matter whether we do one thing or another thing first. So real quick, let me go ahead and make a third set, and we will say that in the third set we have 3, 5, 7, 5, 2, 4. And if we call this A, this one B, and this one C, so it doesn't really matter if we do A, then B, then C, or if we do B, then C, and then do A to the composition of B and C. What that might look like is if we have here, we have 8, 1, that maps to 1, 2, and then that maps to 2, 4. So the composition for A, B, and C would be 8, 4, and I believe that's the only number that actually works out. But it also doesn't matter if we started here at B. If we went from 1, 2 to 2, 4, then we would have 1, 4. But then we would look at A and we would say that we have 8, 1 going to 1, 4. So we would still end up with 8, 4. Now, I don't think that's going to be something that's really important to know, so I'm kind of, glossing over that a little bit. But because it is a question here on the quiz, we're going to say that this is true, that relation composition is in fact associative. Here we're going to say consider two relations. R is a subset of A cross B, and S is a subset of B cross C, which again is what we had. So for example, R is going to be some set with ordered pairs where we have A1, comma, B1, A2, comma, B2, all the way up to A sub n and B sub n. And then we have S is going to be equal to the subset of B cross C, which in this case will be B sub 1, C sub 1, B sub 2, C sub 2, and then again all the way up to B sub n, C sub n. The composition is calculated as CA if there is a B and B such that AB belongs to R and BC belongs to S. And this is only false because this is actually inverted. It should be A comma C. And you can look at that just by saying, okay, here, from what we were just doing, we have A, and then that maps to B, which comes in here, and then we have C. Eventually, when we have our composition, we're going to end up with A sub 1, comma, C sub 1. That is going to be the ordered pair that we're going to be using. Here we have A sub 2, comma, C sub 2. Again, that will all go up until A sub n, comma, C sub n. But this is going to be our composition of R and S. And again, like I said, the order here is going to be A comma C, not C comma A, which is why this is incorrect right here. Here, if a binary relation is asymmetric, then it must be antisymmetric as well. This is true. In fact, I did a video. It's 3.2, which is a proof on the fact that if a relation is asymmetric, it must be antisymmetric. So I'm not going to cover that any more than I already have. Watch that video if you need proof. If a binary relation is antisymmetric, then it must be asymmetric as well. I'm not going to go through and actually prove it, but it is false. P implies Q in this case, but we do not have that Q implies P. And if you go back and watch that video, I'm sure you can probably extrapolate the proof of that. I'm having problems with the audio, so I had to come back and redo some of this video, but that was question number 6. For a relation to be partial order, it cannot have which of the following properties? Well, there are two ways to know this. Either you remember that a partial order relation is simply reflexive, transitive, and antisymmetric. All of these are the properties of being a partial order set. Or if you just remember that a partial order is reflexive, then you know that it cannot be irreflexive. By definition, nothing can be both reflexive and irreflexive. The definition of being reflexive is to have a relationship between x and itself for every value of x. The definition of irreflexive is that for every value of x, it is true that x does not have a relation on itself. So both of these directly contradict each other. You can only be one or the other. They are mutually exclusive. That being said, it is possible for a relation to be neither reflexive or irreflexive. So in this case, the answer is going to be irreflexive because these are the three properties we need to be a partial order set. Number 8, it is possible for a relation to be both reflexive and irreflexive. I said false, and we just talked about the logic behind that. Then finally, we have question 9. If a relation is not reflexive, then it is possible for it to be irreflexive. I was just talking about that, and that is true. So it is possible for a relation that is not reflexive to be irreflexive. And as I was saying, it is also possible that a relationship is neither of them. And then finally, a relation cannot be asymmetric and antisymmetric. This is false. In fact, as we saw in a previous question and in the proof in 3.2, every single relation that is asymmetric is antisymmetric. So this is not only true, it is the opposite of the truth. A relationship that is asymmetric is always antisymmetric. And that was everything. I just wanted to do a quick little review and move on.